Good afternoon, everyone, and welcome to today's FMS seminar. It's my pleasure to introduce our speaker, Dr. Michael Heisel. Michael is a lecturer at the School of Civil Engineering at the University of Sydney. Before this, he was a postdoctoral researcher at the University of California, Los Angeles. He was supported by a fellowship from the US National Science Foundation. He holds a PhD in civil engineering from the University of Minnesota, and his research focuses on turbulent structure and scaling of boundary layer flows, with special emphasis on geophysical applications. And today, Michael will be talking about new perspective on similarity in the atmospheric boundary layer. Thank you, Michael.
Thank you, Oman, and thank you for having me here for the talk, and to everybody in the audience who's joining us, and to all future viewers on YouTube. I'd like to say hi to you as well. Since Aman already shared the title, I don't need to repeat that. But before I do get started, I'd like to acknowledge some key people that contributed to the work I'll be sharing. They include Marcelo Chimecki. He was my postdoc advisor at UCLA. Peter Sullivan from NCAR, National Center for Atmospheric Research in the US. We worked together a bit on stably stratified data that I'll talk about later. And then Gabby Catul, I've worked with closely for a number of years, and he's been a mentor for me. In terms of funding, most of the support for this work came from the National Science Foundation postdoc fellowship that Aman mentioned in the introduction. And then the final acknowledgement before I get into the introduction is that there was a topically similar talk a couple of months ago from Professor John Finnegan. So he also talked about atmospheric boundary layer, turbulence, and mean profiles. However, his focus was more in the vicinity of plant canopies. We'll be looking today farther away from the surface. However, there's a lot of overlapping themes that we'll be talking about. So if you enjoy this presentation and you happen to miss Professor Finnegan's, I'd recommend you check it out on the YouTube channel. So I'm going to spend about 15 minutes or so on a quite lengthy introduction just to set up the problem. And it all starts from the fact that turbulence is complicated, and that's the reason why many of us do the research that we're doing in a number of different flow configurations, including in boundary layers. So trying to make sense of any of these individual features is not really feasible. And another interesting thing, and something that makes it worth studying, is that these boundary layers are all around us. So you can get them across a wide range of scales in both engineering and environmental applications, down to very small scales once you get into biological applications as well. So in nature, this can range from on the order of tens of centimeters up to around 1 kilometer in depth, or 5 kilometers, depending on where you are. And this atmospheric boundary layer that I've pictured here is going to be the focus of today's talk. So this is kind of the largest terrestrial boundary layer that we have. And as I said, making sense of all these instantaneous features in the flow that might be spanning a wide order of scales can be very complicated. And what makes the problem a lot more tractable is the fact that we have a tool in our toolbox known as similarity. So even if we can't make sense of individual features, we can still predict the statistics over an ensemble and understand that they're going to follow the same shape regardless of what the scale is. So even if you're looking at something that's on the order of tens of centimeters or a kilometer in depth. One of the foremost examples of this is the log law of the wall that many of you are probably already familiar with. So this describes the mean velocity within an intermediate region of the boundary layer. So the mean velocity changes logarithmically with distance from the surface. And then the relevant scaling parameter is the shear velocity u star. That's the same as u tau for those of you in engineering. And it is the velocity corresponding to the shear stress at the surface. Now, what I mean by intermediate distance is that the log region is far away from the surface in terms of any roughness or viscous effects, and is also far away from the outer boundary layer. So you're at this intermediate region where neither the roughness geometry or the boundary layer depth have a direct impact on the flow statistics. Now, what happens when we go to the atmosphere is that typically the overall structure of the atmosphere is treated in a very similar manner as these more canonical boundary layers. So if you look at Garrett's textbook, the first figure that you'll see is the one here on the right, where you have an outer layer forming the bulk of the boundary layer, and then some sort of an innermost region where roughness matters, and then an intermediate region that's known as the inertial sublayer. I'll be calling it the surface layer today just for simplicity, but the idea is the same as the log region, where it's far away from the outer condition H and is also far away from the surface roughness. So if we look at a written definition for the log layer and the surface layer, that's pretty much the same. It's the lowest 10% or so of the boundary layer, so far away from the outer boundary condition. The statistics in this region only depend on the surface scaling parameters like the shear stress and the position Z. And in addition, in the atmosphere, you're also neglecting the effects of Coriolis from the Earth's shape and rotation. So if that was all that there was to atmospheric similarity, it would be pretty straightforward and easy. It would just follow the log law. The problem that we have is that there are often temperature differences that change throughout the day. And these temperature differences lead to density gradients that can either enhance or suppress mixing. So in the visualization from the Stuhl textbook here in the bottom left, during the daytime, you typically have convective conditions that form a mixed layer. And during the nighttime, you have what's known as stable stratification. And I'll go into a little bit more detail on each of those later on. Another noteworthy thing is that this is potential temperature, so it's temperature accounting for pressure effects, and you end up having what's known as a stable capping inversion that limits the height of the atmospheric boundary layer. So it's limiting the entrainment, particularly during daytime conditions. So predicting how these temperature differences and density gradients are going to impact the mean flow is something that's been studied for quite some time. And the prevailing understanding for this has come from Monin-Obukhov similarity theory, or MOST, from the 1950s. And the theory speculates that all of the deviations from the log law that are due to these temperature impacts are going to be a universal function of a single parameter, Z over L, which is given the notation zeta. I'm going to explain what zeta is in just a minute, but first explain what I mean by how it's normally formed in terms of the theory. So typically what you do is you take the gradient for the velocity, which from a few slides ago you saw was U star over kappa Z. And if you divide it by the log law scaling, so this parameter here, then the quantity on the left should be equal to 1 when the gradient matches the log law. And then deviations from 1 can be entirely predicted by the effects of stratification or convection. So if phi is greater than 1, that's typical of stable conditions where you get steeper changes in the velocity than what you would see in the neutral log law. And then in convective conditions, phi is less than 1 and the gradient becomes weaker. One of the limitations of the theory is that you have to determine the actual formula for this empirically. It's not determined a priori from the theory itself. And another important note is that all of what I just said about the velocity gradient also applies to the temperature gradient. So d theta dz as multiplied by the surface temperature scaling parameter is expected to behave exactly in the same way. So what is this single stability parameter that's supposed to capture all of these temperature effects? Well, it comes from the Obukhov length from Obukhov in the 1940s. Professor Finnegan talked about this in detail and about how you can get it from dimensional analysis. I'm going to talk about how you can get it or understand it in terms of the turbulent kinetic energy budget. So if you simplify your budget and neglect any of the transport or diffusion terms, you end up getting a relationship or a balance between shear production, buoyancy production from the heat, and dissipation. If you apply scaling parameters to each of these terms, so use the log law scaling for the shear production and surface heat parameters like the surface heat flux for the buoyancy production, and then take the ratio of these two, you end up getting Z over L. So the magnitude of this value tells you how important buoyancy is compared to shear in producing turbulence. And then the sign of it tells you whether or not you're in stable or convective conditions, because that is based on the sign of the surface heat flux. Another thing that's really important about Z over L is that it's entirely consistent with what I said about the surface layer earlier, in that this is a scale that depends only on the position Z and surface parameters. So L is entirely defined by these surface parameters, and it has no influence from things that are deeper within the boundary layer. So in terms of how this theory is used in practice, it's pretty widespread. And one of the most useful ways that you can use this is actually to invert the equation. So instead of solving for phi, you actually solve for the scaling parameter like U star or theta star. And these are directly related to very practical pieces of information like what the shear stress is at the surface or what the exchange of heat or other scalars like moisture are in global models. So oftentimes this is used in large eddy simulations where you have some sort of known value of velocity from your grid resolved data, and then you use that to infer what the surface stress is based on the log law and Monod-Nobokov corrections. And then, as I mentioned, you can do the same thing for the temperature. In global models, this becomes really critical because this is entirely what's capturing the exchanges between the land and the atmosphere. So this is a pretty important piece of the outcome of both weather forecasting models and also climate research models. So in terms of then where do we get the empirical functions that define phi? The answer to this historically has come from field measurements. So Professor Finnegan again talked about this in quite a bit of detail. Normally, this is coming from MET towers or meteorological towers, and data from these towers generally support the existence of some universal function of zeta. So of phi as a function of zeta, I should say. So in convective conditions, zeta is less than 1 and phi, or less than 0 and is negative, and phi is less than 1. Phi becomes 1 and crosses through the log law condition when there is neutral conditions, which is zeta equals 0. And then you typically have that phi is greater than 1 under stable stratification. However, there are some really important limitations to these field measurements that are critical to understand the basis for the rest of the talk today. And that is that if you look at where these towers sit within the atmospheric boundary layer, typically they're on the order of 1 to 10 meters, or maybe a 30 or 50 meter tower if you're lucky. I don't think I've really seen much higher than 100 meters anywhere that's used for atmospheric research. And then consider that the boundary layer depth is often on the order of 1 kilometer. So your towers are usually sitting only within the lowest portion of the boundary layer, and they also have these finite number of points. So if you measure a profile at any given point in time, it's difficult to actually see trends along Z over H because just the scatter and uncertainty in the field measurements becomes greater than the actual fidelity that you have along height. And so if you were to take all of the field measurements and do a scatter plot of where they sit within this parameter space of position within the boundary layer and then the bulk level of convection or stratification, it would maybe look something a little bit like this. This is just my artistic interpretation. Don't quote me on it. And the point and the important takeaway from it is that most of the parameter space from field measurements is spanned along only one of these axes. So it's mostly spanned along H over L at fixed positions of Z that are quite close to the surface. So most of the variability and the accounting for trends that you see in field measurements is actually dominated by functions of H over L. Now, a key consequence of this is that there's not very much information about what's going on farther and deeper within the boundary layer in the outer layer. There is some theoretical understanding of what happens in this region coming from the 70s and 80s, as I'll show later on in the talk. However, the behavior in terms of going from the surface layer to the outer layer is not very well understood. And so to date, at least, some simple assumptions have been made. And By these simple assumptions, what I mean is normally this whole parameter space is just treated using the single parameter zeta that I introduced earlier. So if you take the product of z over h and h over L, you get your Mononobukov stability parameter z over L, and fixed values of this are going to show up like the curved line here. And the assumption is that from Mononobukov similarity theory, you can span the entirety of this parameter space in the surface layer just using this single variable zeta. And as a matter of simplicity, what's been done is assume that the outer layer condition actually starts as at a position where you reach a particular value of zeta. Now, what I hope to do with the rest of the talk is to demonstrate that this last assumption that I mentioned in particular is actually not correct, and that the behavior approaching the outer layer really depends on the boundary layer of depth h. And in particular, transitioning from surface layer behavior where the surface scales are relevant to the outer layer position where h is relevant, this transition starts lower in the boundary layer than is traditionally assumed. So typically, if you remember, the surface layer goes up to 10% of the boundary layer depth. What I hope to show is that even at half of that height, h starts to become a relevant parameter. And so this is going to hopefully show that the reduction of this parameter space into only zeta is insufficient, and understanding what's happening along z over h and h over L requires an expansion to include additional parameters. With that in mind, the rest of the talk, I'll be looking at both of the typical conditions that we get in the atmosphere. So I'll start off with convective conditions, and then later on, I'll spend quite a bit of time talking about the stable results. Okay. So convective conditions, just to give you an idea of what I mean by this. So typically during the daytime, the Earth's surface is more conductive than the atmosphere, so it's going to heat up faster, and you're going to have warmer air at the Earth's surface than the air that's above it. So you end up getting this density gradient that creates thermal plumes that have greatly enhanced mixing compared to just neutral turbulence. And what you end up with is very efficient mixing that creates much more uniform gradients relative to the log law, which as a result of this, you get these derivatives, the du dz, that's much flatter than what the log law would predict. So in terms of our understanding from field measurements, the universal form of the function phi follows some general trends that are fairly consistent across different authors. And specifically what I mean is that if you plot your dimensional gradient, the gradient relative to the log law versus this stability parameter, you expect that all of your data is going to collapse along a common curve. However, the exact form of the curve depends on what study you're reading. All of the forms will cross through 1 when zeta is equal to 0. That's because it has to abide by the log law under neutral conditions. And then all of the forms approach some sort of a power law when zeta becomes very large. The difference between them is the exact power law exponent, which is a matter of what the scaling in free convective conditions is, but that's not going to be the focus of today's talk. So any one of these three will do for our purposes, and I'll be using the Businger-Dyer relations moving forward just because this is quite a popular empirical function used in atmospheric sciences. So from field measurements, there's fairly good support for a universal function of phi as a function of zeta alone. However, once you start to look at simulations, you start to see these consistent discrepancies. So with the field measurements, what I mentioned with the number of finite points you can have along a Met tower is that usually any trends along z over h get lost in the scatter of the rest of the data points. However, this information is much more detailed in simulations. So if you look at trends across different cases, they do tend to follow the Mononobukov similarity fairly well, but then within each individual profile, there's a steeper decay than what you would predict, such that you can't actually collapse all of the data points along a single curve, because within each individual case, it's decaying more steeply. The first group to point this out, coming from Khanna and Brasseur in the late 1990s, the one on the left, they specifically suggested that in order to account for these trends, you need to expand the parameter space of phi to include the boundary layer depth. And that's going to be the approach that we use moving forward as well. So in order to look at this, I conducted large eddy simulations under convective conditions on a 1024 squared by 512 grid, ranging from weak convection to moderate convection. The corresponding bulk values of H over L are given here on the right. For all of these conditions, you note that there is an extensive uniform region where the velocity isn't changing. This is known as the mixed layer, and I'm going to come back to it in a couple of slides. So if we take these profiles and plot them in the dimensionless form, so we have our dimensionless gradient versus the stability parameter, the Monin-Obukhov parameter, we see a similar trend to what I just reported from previous literature, where you can draw a nice line through all of the cases, but then within each individual case, the decay is steeper than what would be predicted from the theory. In particular, what I've done here is plotted both within the traditional surface layer, so in the lowest 10%, but then I've also included the region above the surface layer, just to give you the context of what's happening as you continue to move up. And in particular, what you're seeing is that this steeper decay is becoming more and more accelerated as you move farther away from the surface. However, there isn't really any trends that you can tell in terms of where this gradient is decaying and being cut off, at least in terms of the stability parameter. If we instead normalize this plot by the relative position within the boundary layer, you can now see that all of that decay is reaching a common point that's approximately at 40% of the boundary layer depth. So around this height, all of the gradients are going approximately to zero and are falling off this logarithmic plot. So if I go back to the dimensional profiles that I showed a few slides ago, where I noted that we have this uniform region, I've now put dashed lines at 0.4 H, and you can see that this is does a pretty good job of characterizing the start of this mixed layer. And within this mixed layer, we have free convection, meaning that there is no shear present. The mixing is complete. The velocity and the temperature are uniform, and because you don't have any shear, the U star and Z are no longer relevant scaling parameters anymore. So somehow the gradients from the surface are approaching this condition that's being imposed at the start of the mixed layer. So if we go back to the previous slide, and look again at these decays in the gradients, we can now interpret it as an extended transition going from surface behavior at the start of the lines towards the start of the mixed layer at the bottom of the lines as they hit 40% of the boundary layer depth. So in order to account for this decay as a function of Z over H, I did a fairly simple approach of just adding an exponential correction. This is not meant to be the final similarity expression that I'm proposing. It's more an ad hoc correction where the purpose of it is to demonstrate that you can improve your result if you include Z over H, such that we can then in the future work to fine tune this in a more precise manner and get something that matches the data better. So really the purpose now is just to show that this correction and the second parameter are necessary. And this correction is specifically multiplied to a Businger-Dyer type relation that has a -1/4 power law. So now I'm going back to the functions of phi as a function of zeta, and I've corrected phi using this exponential correction that I just showed. And after you apply the correction to account for this decay, you can see that there's significantly better agreement across all of the cases within the surface layer. There is still a lot of discrepancy farther away from the surface, so approaching the mixed layer. And this is just again to note that it's a preliminary effort and more will be done in the future to fine tune it. But importantly, you see a significantly better result in the surface layer than what we previously had. So to summarize this part of the talk, I'm going to first just recap what the traditional understanding is for Mononobukov similarity theory and its application in field measurements, where you have this parameter space that has a bulk level of convection, a position within the boundary layer, and then some sort of a surface region where you're assuming that H doesn't matter. And the tradition is to map this parameter space using the single variable zeta, and the cutoff as you approach free convection is typically taken to be zeta on the order of -1. So even if the start of free convection is above the traditional surface layer, it's often assumed that you can still use this zeta parameter. What we're seeing in today's results is that there are a couple of considerations that need to be made in this case, and not just one transition to local free convection. And this is that you have global free convection in the limit of H over L. So this is basically representing when you have no mean wind anymore and the temperature differences are completely dominant. So mapping that part of the parameter space, at least for now, I've done this using the traditional Businger-Dyer relation. So as zeta goes to infinity, so does H over L, and you approach some sort of a global free convection limit. However, what we're also seeing here, importantly, is that we have this mixed layer where you have no shear present, and this mixed layer is imposing a boundary condition at 0.4 H, and transitioning from the surface layer to this mixed layer starts below 0.1 H. And so you have to incorporate H into the similarity equations in order to account for what's happening, at least in the upper half of the surface layer. Okay. And this transition is captured using this exponential cutoff correction that I introduced. So that's the convective result. And I'm now going to walk through the stably stratified result in a little bit more detail. And in this case, you have a cooler Earth surface and cooler air at the surface of the Earth and warmer air above it. So this creates a stably stratified boundary layer where the density gradients are opposing any turbulent mixing. So you actually get less mixing than neutral conditions. And as a result, you're allowing your boundary layer profile to become steeper than it would if you had the neutral condition and the log law. So your boundary layer gradient is going to be greater than phi is equal to 1. So in terms of our understanding from field measurements in the stably stratified case, there is also general agreement in this regime as to the general form of the equation. Initially, most of the analysis was focused on small values of zeta. So from the Kansas experiments from Businger and Dyer, and later reevaluations from Hagström, the general idea was that at small values of zeta, you have some sort of a linear trend. And then more recently, researchers have been pushing the boundary of what values of zeta are being tested. And as you go beyond 1, the consistent trend is that there's some sort of nonlinearity where the phi value is starting to drop off. So I'll show just 2 examples of the earlier and the more recent, where the Businger-Dyer that I showed from before, the linear relation here matches pretty well with the measurements. But as you can see, hopefully on your screens, the range of zeta values is really less than 1 in this case. The more recent result from Chen and Broussard, now you have 1 zeta equals 1 approximately here. And so as you push to higher values, you see that the phi value starts to drop off considerably and plateau. They came up with an empirical equation for this that's given here at the bottom of the screen. So this is actually the one that's used in weather research and forecasting models, and it does work well empirically, but the actual physical meaning of it is it doesn't really have one in terms of the phenomenology. And so hopefully we'll be able to replace this today with something that's a little bit more physically meaningful. And in order to look at the stable conditions, I used previous simulations. So these are from the colleague that I mentioned at the beginning, Peter Sullivan from NCAR and his co-authors. He did simulations on a 1024 cubed grid and published them in Journal of Atmospheric Sciences in 2016. And I'm just using some of the statistical results from that he generously shared. And just an example of a slice of the temperature plane is shown here on the right-hand side, just to give you an idea of what it might look like. And to give you an idea of the mean profiles, these are the dimensional mean wind speeds. This is the magnitude of the wind speed, so it's considering both the X and the Y direction. In the atmosphere, you have Coriolis effects that become relevant as you move farther away from the surface. And so this is kind of, to some extent, undoing that effect and just trying to take the net impact of the wind speed. One of the things that you'll immediately see is that the shape is significantly different than convective conditions. You no longer have the uniform layer throughout most of the boundary layer and is replaced by something that has quite a steep gradient. And this gradient, as you can see, is becoming steeper and steeper as you increase the stratification. Another thing that you'll note is the presence of a low-level jet, and the presence of this jet is actually forming the top of the boundary layer and determining its depth in the stable case. Finally, conventionally neutral. This means that there's no cooling or stratification imposed at the surface. All of the cooling comes from the stable capping inversion at the top. So you're very close to neutral throughout the lowest portion of the boundary layer, and any low levels of stratification are coming from the top down from your capping inversion. And I'm going to primarily focus on these surface forced stratified cases in the colored lines, and then only towards the end, I'll bring back the conventionally neutral case. Okay, so after looking at the mean profiles, what do the gradients actually look like compared to Monin-Nabokov similarity theory? And so again, we have our non-dimensional gradient, so du dz relative to the log law, as a function of this similarity or scaling stability parameter zeta. If Monin-Nabokov similarity holds, these should all collapse on a common curve. And you see that in terms of their shape, they're all generally following the same shape. That's somewhere in between Businger and Cheng and Broussard. However, there is a notable and robust stability trend in these results. So within the lowest 10% of the boundary layer, it's present, and then it is also present at higher positions above the traditional surface layer. Specifically, what happens is that if you're at a matched value of zeta, as you increase the bulk stratification, your values of phi become smaller. So how can we understand what's happening in the stable case? And to do that, we're going to use the convective case as a guide, just to recap what we already saw earlier. And what I had mentioned in the introduction is that we've, in the community, have known since the 70s and 80s that the bulk of the convective boundary layer is a mixed layer where you have no shear. However, traditionally, the assumptions have always been that you only reach that condition once you get to values of zeta on the order of 1. So it's assumed to be scaling with zeta in many cases. You have something very similar in stably stratified conditions. It's been known for quite some time again that the outer layer is dominated by what's known as Z-less scaling. And the assumption has typically been that the onset of Z-less scaling is occurring at values of Z over L on the order of +1 in this case. So Z-less scaling essentially means that the gradient becomes independent of Z, and that means that it reaches some sort of a constant value. And as a result of it being constant, the actual velocity profile becomes linear in nature. So you can see that this works fairly well at describing the stable cases here, in that they look quasi-linear throughout a lot of the boundary layer, even in this conventionally neutral case. The only difference is that the slope is changed. So the simplest first order approximation that we can make for what this Z-less gradient should be can come from the limit of the most stably stratified case we can achieve. In this case, we can assume that the entirety of the boundary layer is just a linear profile where Z doesn't matter. In that case, the definition for the gradient is forced based on boundary conditions to be U infinity, or the geostrophic wind speed, the free stream wind speed, divided by the overall depth of the boundary layer. So this is just a simple linear approximation for the entire boundary layer. And what I'm going to do now is come up with a very simple model for transitioning between what's happening at the surface to this first order approximation for the z-less gradient. So here is the model. It's pretty straightforward. What happens is that if z is small, if z is small, this first term becomes large and dominant. And so towards the surface, the log law term is governing the behavior. And that's where you get this sharp decrease close to the surface. And then as you grow larger in z, eventually the log law value eclipses the z-less constant, and this constant term becomes dominant and determines the overall behavior in the outer layer. And you can see that there's a significant fall off in the gradient, and it reaches something that's approaching a constant value. If we replace this constant with z infinity over h, we can evaluate the model here, applying now normalizing the gradient versus u infinity over h. And you can see that this very simple model works pretty well in that it overlaps nicely with the data close to the surface, in that you can't even distinguish the lines, and then it plateaus at the right location. I have added just a correction factor here just to allow for any inaccuracies in this first order approximation, and then that factor will be determined by fitting to the data in just a couple minutes. In order to proceed, though, we don't want this dimensional profile, we want the non-dimensional one. And so we can divide everything by the log law scaling parameters, u star over kappa z. In this case, the left-hand side becomes our non-dimensional gradient, the log law contribution becomes 1, and then our z-less constant actually becomes a linear term that depends on some sort of a drag parameter, u infinity over u star, and then where within the boundary layer you are. So how far away from the surface you are relative to the overall depth. Now, we don't want u infinity in our final equation, and so we want to be able to replace it. Typically in engineering, u infinity over u star or u tau would be a function of the Reynolds number. However, in the atmosphere, which is typically considered the asymptotic high limit of Reynolds number, the more important dependence is actually the stratification or the convection. So if you're looking into the literature about this, they might call it something different. Sometimes it's known as Rossby similarity, geostrophic drag, or resistance, but it's all talking about how this drag parameter varies as a function of the stability. And what we see from the Largetti simulations anyway, is that there's a fairly nice square root relationship that we can use. So if we put this square root of h over L into our drag parameter here in the model, we can simplify it down to z normalized by some sort of a length scale that's a combination of the depth h and the Obukhov length L. So it's the geometric mean. Now we can evaluate this model that I showed in the previous slide. So this is the final model where now C, the value for C, is coming from fitting to the data. And what you can immediately see where you're introducing this new mixed length scale is that there's significantly better agreement across the entirety of the range that I'm showing here, which is from about 3% of the boundary layer depth up to around 30% of the depth. So it's working very well within the surface layer, and then it's working a little bit less well in the outer layer, but it's still significantly better than what we had before. We can actually improve what we have in the outer layer by considering an idea known as local scaling. So this comes from Neustadt in the 80s, where the idea is that you can get better statistics and results if instead of applying surface scales, so the surface shear stress or the surface heat flux, you replace it with the local and height fluxes and shear stresses. So this is the turbulent shear stress or the momentum flux, and then the local heat flux. So now the plots are normalized. The non-dimensional gradient is normalized by the local momentum flux, and the local Obukhov length is defined using local momentum and heat fluxes. And what you can see is that there's better agreement within the outer layer, and everything has now become more linear in nature. So this linear approximation that I have from the preliminary model is working quite well. The other really noteworthy thing here is that I've actually added in the conventionally neutral case, the black line here that's sitting at the bottom. So again, this is a case that has no buoyancy or stratification at the surface, and it's only very, very weak within the surface layer and within the lower portion of the outer layer. And so even though you have this very weak top-down non-local stratification, this model that I'm implementing does a remarkably good job of matching it up with these other cases that actually do have surface-forced stratification. So this gives me some confidence in this result working. I also did a comparison of field measurements for this particular study, but I just don't have time to present them here today. Okay, so going back to the same phase space that I talked about, where I was talking about the convective results, I'm going to summarize here in a very similar manner for the stratified results. So we have our position within the boundary layer, Z over H, and we have our bulk level of stratification, and we have these scaling regimes where we know we have surface scaling, and then we know we have Z-less stratification somewhere farther away. What is typically done in Monod-Obukhov similarity is that you assume that this transition going from 0, 0, so where the log law is valid, out to the Z-less stratified region is occurring as a universal function of zeta, and the onset of Z-less stratification is zeta on the order of 1, where the lambda here is the local Obukhov length. What we're seeing is that even in neutral conditions, as long as you have a stable capping inversion at the top of your boundary layer, you're going to achieve Z-less stratification somewhere within the bulk of the outer layer. And this forces you to transition from going from surface scaling to Z-less stratification as a function of Z over H. So the portion of the model here on the left is the log law transitioning to some sort of a Z-less condition as a function of Z over H. And then what's actually changing as a function of bulk stratification is that the intensity of this gradient is becoming steeper. Now, by intensity, I mean relative to the log law, so it depends on what the U star parameter is, because all of this is considered to be normalized by U star. So if you look at weak stratification, you're going to have a relatively shallow gradient. And then if you look at stronger stratification, it'll become steeper and steeper and steeper. And this is reflected in the geostrophic drag relation that I introduced to replace U infinity over U star. Okay. Now, what we can do, just because of the units and the parameters combine nicely, you can actually reduce this into a single parameter that just becomes a mixed length scale in order to go all the way from the surface scaling to the Z-less stratification. So that's most of the results, but before I wrap up, what I want to do is revisit the definitions I gave for the log region and the surface layer, and then offer some sort of an interpretation of how I see the results fitting within this definition. So specifically, what we've seen is that probably one of the first 2 points is incorrect, in that we see that the boundary layer depth H is a relevant parameter below 10% of the boundary layer thickness. The possibilities arising from this are that H is always relevant throughout the entirety of the boundary layer. And another possibility is that maybe the surface layer is just not as deep as is traditionally assumed. I'm going to move forward with the second possibility. I think that this one is somewhat more likely, at least from a simple explanation. It may be more complicated than this. And I'll close out by showing a visual of what I mean by the surface layer being shorter. So if you're looking at a canonical boundary layer, or in engineering applications oftentimes, in order to define the log region, you have to assume that it's far away from some outer boundary condition where you have no shear and you have some sort of a free stream velocity. And as a result, you have this range of heights that's far away from the depth of the boundary layer H. What's happening when we add any level of convection or stratification is that even in relatively weak conditions, most of the outer layer is becoming entirely dominated by these buoyancy effects, such that instead of the boundary layer all the way at the top mattering, it's actually a condition that's much closer to the surface layer that's beginning to impose on the statistics that are at the top of the surface layer. Specifically for convective conditions, this is that you reach a zero shear condition in the mixed layer that's approximately at 40% of the boundary layer depth. So the onset of this is determined by H. And then similarly, in stable conditions, you have the onset of Z-less stratification, where the bulk of the outer layer, the gradient is a function of H in a direct manner. So in order to actually be able to neglect H as a relevant parameter, you may need to assume a region that's far away from these lower boundary conditions. Specifically, this might result in a boundary or a surface layer that's only occupying the first couple percent of the overall boundary layer thickness. And all of this is not due to any sort of momentum effect, but it's all entirely due to effects of buoyancy. And in this context, what I showed you today would fall under this intermediate region. So it would fall under this red square region that accounts for a transition going from surface scales very, very close to the surface to some sort of an outer layer that is dominated by buoyancy. And I can't actually say from the results that I have how close to the surface layer might go, just because there are limitations in the resolution of the large eddy simulations that I employed. So that concludes the talk, and I'm just going to very briefly summarize before handing it back over. I showed that in order to account for the mean profile dependencies in the atmospheric boundary layer, whenever there's buoyancy present, you need to incorporate the boundary layer depth H. This is specifically for trends that are between about 5 to 30% of the boundary layer thickness. That's the range of heights that's represented here in these comparative plots. And the reason for this is that you're accounting for going from the surface to a buoyancy-dominated outer layer that's governed by H. And you can see that compared to the traditional theory, you get significantly better agreement and similarity across cases. One of the things that I was not able to do for the sake of time is show you the temperature results, at least in a step-by-step manner. However, if you'll give me the benefit of the doubt, the temperature is the same in terms of the arguments. There is a mixed layer throughout most of the convective boundary layer in terms of temperature profile, and you also have a Z-less stratification in stably stratified conditions for the temperature profile. So before wrapping it up, I'm just going to quickly jump to the end result of the temperature. Here, phi h is the similarity relationship for heat. And you see that very similar to the velocity, you get a much better result when you incorporate h as a parameter than when you are neglecting it. If you're interested in more details, I'd refer you to the relevant publications for each of these cases that I'm showing here. And now I'll turn it back over to Aman for the question and answer. Thank you for your attention.
Thank you, Michael, for this insightful talk on atmospheric boundary layer. We invite the audience, if you have any questions, please feel free to unmute and ask Michael any comments or questions you have, or if you prefer, you can also type on the chat box.
While we are waiting, may I ask a question?
I see a hand up. Oh, no, it's clapping. Sorry. Go ahead, Azadeh.
Okay, so Matt, do you want to go first?
Yeah, sorry, that was supposed to be a hand up and also clapping earlier, but you can hear me?
Yes, thank you.
Great. Thanks. So that was really interesting. So yeah, caveats is I'm not much of an atmospheric person or even an engineer, but how well do these like wall models work in the LES for like situations where you're studying kind of the effects of strong stratification, or maybe is this not like super strong stratification?
So normally the wall models are applied at the lowest grid point within the domain. And in a lot of cases for the global models, that's on the order of meters or tens of meters. So I gave that as a guiding motivation, but in reality, at that height, you're actually more likely to be worrying about the effects of the roughness and canopy and things of that nature. So normally those grid points are actually at quite a small percentage of the overall boundary layer depth, where the results that I'm showing you here today are potentially a little bit less relevant, but this is still very important for coarser simulations where the first grid point might be higher in the boundary layer, or for just single column models where you're making assumptions about behavior spanning the entire boundary layer.
Mm-hmm. Thanks.
So I may ask one question. So Michael, thank you so much for the interesting talk. One thing I was thinking, the location of the transition from surface layer to outer layer, what you see in your results is that it's very much affected by the buoyancy. Do you think there will be, or it will also be a function of the surface as well? So if we have the big roughness canopy, the terrain changes, that would also affect where this transition is happening? Or do you think it's mainly really just the buoyancy that's
I think it would mainly be the buoyancy and the depth of the boundary layer. So ideally, if you have roughness that is small enough relative to the surface layer, the only impact of the roughness once you get into the inertial sublayer, which is far enough away from the surface, or the log region, as you might call it, the only impact of the roughness is the bulk shift in the profile due to the excess drag U star and due to the roughness length Z naught. Those shouldn't actually impact the shape of the profiles once you get above the roughness sublayer. That is what the focus of Professor Finnegan's talk was a couple months ago. The caveat to that is that if you have really, really rough conditions, your roughness sublayer can actually completely eliminate the surface layer or the log region and start to interact directly with the outer layer condition. So that would be more of a circumstance that's breaking the expected overlap region that we're developing in these assumptions.
Yes.
Maybe I can ask more of technical detail question. So when you show the velocity profiles in slide number 21 or the other slides, at the top, I see that there was strong gradient. Could you explain it?
Which slide number did you say? I'm sorry.
21, for example, number 21.
21. Excuse me while I go back. So the strong gradients at the very top.
So you have the zero gradient of the velocity profile, then suddenly changes.
Yes. So this is a mixed layer, and then you also have the free atmosphere above it. The velocity, the wind speed in the mixed layer is not exactly the same as what's happening in the free atmosphere. There's some difference, and that difference is spanned by the behavior in what's known as this entrainment region. So this region is essentially a combination of the mixed layer and the free atmosphere. And so the result that you get is something that is going to transition between the two of them. And so if you're predicting what the mixed layer wind speed is going to be, it's usually, it doesn't scale like this, but it's usually a majority of the free stream atmosphere, but not the entire free stream atmosphere. So you still have to have a jump in velocity in order to reach the free stream condition.
Okay.
I don't know how well that answered it, but it has to do with the stable capping inversion that's at the top of the boundary layer and how the flow within that capping inversion is interacting with plumes that are being ejected out of the boundary layer.
Okay.
But that's something that is very interesting, but outside the scope of what I was concerned about with this talk.
Well, thanks.
I guess it seems like we could perhaps wrap it up. I don't see any more questions.
Michael, I might just ask you one question.
Okay.
I'm Matt from the University of Queensland. It's actually, if you go forward a few slides, you showed that there was a change recently where people have been able to observe higher in the atmosphere in the stable conditions to go to higher Z on L values.
Yeah. Here.
Yeah, and I think when you have the right, yeah, that one. So the Cheng paper, what is it that's allowed people to now go higher than what they were able to do previously? Is this like a transition to using LiDAR as opposed to point measurements or something like that?
It's a combination of things. Some of it is using taller Met towers. So these measurements in particular are from CASES 99 measurements that used a 30-meter tall Met tower, and the analysis procedures since the 70s and the instruments that you can use have advanced since that time. And so you can use more sophisticated methods to extract specific regions of interest. I think one of the things in particular that's happened is that people no longer use very large averaging periods for very stable conditions, just because the turnover time is so short. And so isolating shorter averaging periods usually allows you to get higher values of zeta. Another consideration is that there have also been campaigns occurring in more polar regions. So some of these, specifically, I think Grachev, for instance, has done a lot of measurements more in polar regions where they're going to have stronger stratification just because of the weather conditions.
Okay, all right, thank you.
Perhaps I can ask another question if I may.
Sure.
You said that you did LES simulation, right? So in terms of, so this is an inflow outflow setup of your domain. If that's the case, then how do you set up your inflow conditions?
So all of the simulations are periodic in the horizontal directions. So the outflow becomes the inflow. And so the idea of it is that you choose a large enough domain that the periodicity doesn't start to contaminate the results. With stable stratification, that's relatively easier just because the size of the structures is quite small. In convective conditions, it's a little bit trickier just because you can get these very elongated structures. And so our domain in the convective conditions was actually 12 kilometers by 12 kilometers by 2 kilometers. So it's very wide compared to the height, just to account for the aspect ratio of the turbulence that's passing through and looping periodically.
Okay. So it's not unlike the standard boundary layer. So you have a constant boundary layer thickness. It's not evolving with distance.
There is some growth of the boundary layer over time, not as much with distance, but you see it over time. And that's just due to entrainment effects that I mentioned with the mixed layer. And you can also, the same thing can happen in the stably stratified. You actually get that the boundary layer becomes smaller and smaller. And typically how these are the same as forced conditions in engineering. The main change is that you're adding a temperature inversion at the top of the domain, and you're also adding some sort of a surface heating or cooling effect. So the convective simulations use a constant surface heat flux, and the stable simulations use a constant surface cooling rate in terms of Kelvin per hour. And those are fairly standard techniques within the literature.
Okay. Thanks. So if there are no any more questions, perhaps we wrap it up here. Thank you, Michael, for finding the time to share us your research.
Thank you for having me.
Yeah. Wait a minute, this chat. Okay, it's just people are thanking you for your